we have learned that a switch is the most essential element in a power electronic circuit. What are the other desirable elements? Inductors and capacitors, which help shape up the current and voltage waveforms. We have also seen how to draw the voltage waveforms in a power electronic converter in which there are only switches. We just need to know the condition of each switch. Is it on or off? And we need to apply KVL in each state. What do we mean by state here? A state represents a combination of the switch conditions. For example, S1 on, S2 on, S3 off, S4 off is a state in our previous examples. So by applying KVL, Kirchhoff's voltage law, in each state, we can get a relation between the voltage that we need, that is the output voltage, and the voltage that we have, which is the input voltage. Once we know the relation, we can plot the waveform of the desired voltage. That is precisely what we have done in the discussion on 4 basic power conversions. But when we add inductors or capacitors or both to a switch network, how do we analyze such a circuit? What do we mean by analyzing a circuit? We intend to look at the waveforms of voltages and currents within the circuit and quantify the nature of the waveforms. From the basic circuit theory, we know that the waveforms of voltages and currents in a circuit look different in transient condition when compared to steady state condition. This is true when we have circuit elements that bring in time while relating the voltage and current. For example, while relating the voltage and current corresponding to a resistor, that means the voltage across and current through the resistor, we use Ohm's law. V is equal to IR. But when the current through an inductor needs to be expressed in terms of the voltage across it, we use L dI by dt. So we are bringing in time here. Similar is the case with the capacitor, where the current through a capacitor I is equal to C dV by dt. It is good to indicate the current directions and polarities of voltages here. So this is how it is defined in the case of resistor, inductor and capacitor. And we know that power electronic circuits invariably contain inductors or capacitors or both. So we will have both transient and steady state conditions for any given power electronic circuit. As far as this course EN313 is concerned, we intend to analyze and quantify the voltage and current waveforms in a power converter in steady state. Let us try to understand what we mean by steady state here with some examples. Consider an RL circuit connected to a DC voltage source. Given an initial condition that the current in the circuit I is equal to 0 at time is equal to 0, we know that the current in this circuit rises exponentially. And it reaches a value close to V by R within a duration of approximately 4 time constants, 4 tau. And what is tau? Tau is equal to L by R. We typically refer to this current rise interval, the interval marked in green, as the transient interval and the other interval as steady state interval. In the steady state interval, we can see that the variation of current is not much and is within some tolerance level. It could be 2% of the final current or 5% of the final current, like that. So this is the first example of steady state where the physical quantities voltage or current do not change appreciably with time and always lie within some tolerance level. The tolerance level is also shown here for more clarity. Now let us consider the second example of steady state. What happens if we connect the same RL circuit to a sinusoidal voltage source? Again, with the same initial condition of zero current, we can show that the current follows this kind of shape with respect to time. You can prove this mathematically by solving the differential equation Vm sin omega t is equal to Ri plus L di by dt. As we all know, the solution to this differential equation has two parts: complementary function and particular integral. The complementary function is an exponential and the particular integral is a sinusoid. The particular integral gives the steady state part of the current waveform, while the transient part of the waveform is the sum of the complementary function and the particular integral. If we look at the steady state part of the waveform, the current is varying with time but in a sinusoidal fashion. So this is the second example of steady state where the current or voltage, current in this example, changes with time but in a sinusoidal fashion. This condition of steady state is popularly known as sinusoidal steady state. However, in power electronic circuits, the currents and voltages are time varying for sure, but not necessarily in a sinusoidal manner. So we need to have a more generic definition of steady state here. We define something called periodic steady state, where all the voltages and currents are periodic functions of time. That means if I1 of t represents a current in a power electronic circuit, a current flowing in an element in a power electronic circuit, then I1 of t plus Ts is equal to I1 of t under periodic steady state, where Ts is the time period of I1 of t. That means if this is the current waveform under periodic steady state, so I1 will have the same value. I1 is the current waveform versus time. I1 will have same value after every period. So if this is I1 of t naught, this will be I1 of t naught plus Ts, and this is I1 of t naught plus 2Ts, and all of them will have same value. Here are a few more examples of the waveforms in power electronic circuits under periodic steady state. V1 is a trapezoidal waveform. Again, it has a period of Ts. Similarly, I2 is a current waveform. Even though I2 is not a well-known shape, it is definitely in periodic steady state. I2 of T2 is equal to I2 of T2 plus Ts. So this condition, the periodic steady state condition, together with the properties of circuit elements, inductor and capacitor, will help us arrive at some interesting results which are useful for the analysis of voltages and currents in a power electronic circuit. Let us consider the waveform of current through an inductor in a power electronic circuit. IL is the current through the inductor and VL is the voltage across the inductor. The power electronic circuit is shown here schematically. So there are other circuit elements that are also present in the power electronic converter. However, we are looking at one particular inductor and the current through the inductor is IL, the voltage across the same inductor is VL. How are VL and IL related? VL is equal to L di by dt, L d IL by dt. Or if you want to express the current in terms of voltage, IL is written as 1 by L integral V dt, VL dt. An appropriate way to represent the integral is minus infinity to t VL of tau d tau. Tau is just the integration variable. This includes the initial condition, which we usually employ to evaluate the integration constant. So IL of t can be written as 1 by L integral minus infinity to t naught VL of tau d tau plus 1 by L integral t naught to t VL of tau d tau. We have just split the integral. So minus infinity to t naught is one part and t naught to t is the second part. And the first part is nothing but the initial condition, IL of t naught. So now IL of t can be expressed as IL of t naught plus 1 by L integral t naught to t VL of tau d tau. Using this expression, we can write the current at any other instant. So IL of t naught plus Ts, let us consider IL of t naught plus Ts. That can be expressed as IL of t naught plus 1 by L integral t naught to t naught plus Ts VL of tau d tau. But from the condition of periodic steady state, we know that IL of t naught plus Ts is equal to IL of t naught when Ts is the period of the current waveform IL. So using this condition, IL of t naught plus Ts is equal to IL of t naught, we can show that 1 by L integral t naught to t naught plus Ts VL of tau d tau is equal to 0. And the value of L and Ts, they are non-zero. So instead of L, we can actually write Ts, that is equal to multiplying by Ts and dividing by Ts. We can say that 1 by Ts integral t naught to t naught plus Ts VL of tau d tau is equal to 0. So what does this mean? This is nothing but the average value of the inductor voltage VL. So we can conclude that in periodic steady state, the average voltage across an inductor is 0. This is a very useful result which we can apply to evaluate different voltage waveforms in a power electronic circuit. We have shown that in periodic steady state, the average voltage across an inductor is 0. This is also known as the principle of volt-second balance. Volt-second, the term volt-second is used because we are integrating voltage with respect to time. By similar arguments, we can show that the average current through a capacitor is 0 under periodic steady state. Why? Because I is equal to C dV by dt. So this principle is known as the principle of ampere-second balance. Ampere-second is nothing but charge. If you integrate current with respect to time, you will get charge. So the charge deposited on a capacitor is equal to the charge depleted under periodic steady state. So what if they don't match? The voltage across the capacitor keeps rising, which is not a steady state condition. So the voltage should come back to the same point. Voltage of the capacitor should come back to the same point under periodic steady state. That is what we mean by this charge balance. So these two conditions of periodic steady state, which talk about the inductor and capacitor, the volt-second balance and the charge balance, along with KCL, KVL, and the switch states, whether a particular switch is on or off. So all these three things will be useful in the analysis of voltage and currents in a power electronic circuit. We will try to understand this with one simple example. Let us consider the example of AC to DC conversion, and we have two circuits here. Each circuit has two switches. But in the first circuit, the left side circuit, there are only two switches and AC source, and R is a resistor which represents the load. In the right hand side circuit, we have an AC source, two switches, and then an inductance L, and then we have the resistive load. Now what are we interested to find? We are interested to find the average voltage across the load, VR average. Why? Because it's basically AC to DC conversion, so we are interested about the average value at the output. But the switching pattern, the states of switches are same in both cases. So S1 is on and S2 is off when Vin is greater than 0. Vin is a sinusoidal voltage, so it will have both positive and negative values. So whenever Vin is positive, S1 is on, S2 is off, and S2 is on and S1 is off when Vin is less than 0. So let us try to see how to find this VR average. So when S1 is on, in the first circuit, when S1 is on, if you apply KVL, we'll see that VR, the voltage VR is equal to Vin. That is nothing but Vm sin omega t. When S2 is on and of course S1 is off, VR is equal to 0 because this S2 is closed, so this load is short circuited. So if you plot the waveform of VR, it will look like this. It is equal to the sinusoidal section in the first half, positive half, and then it is 0, and then again it is positive, it goes on. So what is the average value of this waveform? The average value can be found by integrating it over the complete period and dividing by the period time. That is, VR average is equal to 1 by t integral 0 to t VR dt. So we can show by mathematics that it is equal to Vm by pi, where Vm is the peak value of this input voltage. Now let us see the second circuit where we have an inductor here. So again we do the same thing. When S1 is on, we try to apply KVL. Now since we have another element, we need, if you want to apply KVL, you need to define a voltage across that element. So VR is the voltage across resistor, which we are interested in, and VL is the voltage across inductor. And when S1 is on, if you apply KVL, it is Vin minus VL minus VR is equal to 0, or VR is equal to Vin minus VL. That is in the first half, 0 less than t by 2. When S2 is on, in the negative half, VR is equal to VL because this loop gets closed like this. So the average value of VR is 1 by t integral 0 to t VR dt. So you have to split this integral because VR has different expressions in the two intervals. So 0 to t by 2 it is Vin minus VL, and t by 2 to t it is minus VL. Now if you rearrange this integral, the first part is 1 by t integral 0 to t by 2 Vin dt minus this VL is present in both integrals, so you can merge them and write like this, 1 by t integral 0 to t VL dt. This is, the second term is nothing but the average value of inductor voltage. From the rules of periodic steady state, we know that the average voltage across an inductor is 0, or the volt seconds are balanced across an inductor. So setting the second term to 0, the first term, if you evaluate the first term, you will again get Vm by pi. Of course, the waveform of VR will be different from that in the first case. How do we obtain the waveform of VR in the second case? We need to derive expressions for the voltage VR, which is I times R. That means we have to formulate the differential equations, because L is there in the circuit, we will end up with differential equations. So equation 1 shown here, IR is equal to Vm sin omega t minus L di by dt. This needs to be solved in the interval 0 less than t by 2 with some given initial condition. And then in the second interval, t by 2 to t, you have to solve another differential equation, IR is equal to minus L di by dt. By solving these two differential equations, you will get I, and then you can multiply R to get the voltage VR. But if you try to derive these expressions and then try to get the average value of VR, it's going to be a very tedious process. So the principles of volt-second balance, the periodic steady state principles, will help us arriving at a quicker and easier solution for the voltages and currents in a power electronic circuit. This example here is taken to demonstrate the usefulness of principles of volt-second balance, and similarly you can also apply charge balance in the analysis of power electronic circuits in periodic steady state.